Hi, my name is Michael Minkler. I'm a third-year PhD student at Auburn University. Polymers are so integrated into our everyday lives that it is difficult to look around and not see a polymer implemented somewhere into the materials that you're looking at. Some are so important that we could not maintain our current standards of living without them. Can you imagine living without Teflon? Or without polystyrene butadiene? Or even without polyethylene? Life would be much more difficult without them, wouldn't it? The invention of these materials brought on the new age of technology and also raised the bar to our current standards of living. But as society's demands continue to increase for cheaper, more accessible, and more functional technology, the materials used in these devices must also change. This brings us to the next step in materials engineering: conductive polymers. Polythiophene, polypyrrole, and polyaniline are all three conductive polymers. Today, however, we will discuss only polypyrrole. As you can see, it is similar in structure to polythiophene, but it has a nitrogen incorporated into its aromatic ring, much like polyaniline has a nitrogen on the side. It was first synthesized in 1963 by McNeil and co-workers through the pyrolysis of pyrrole. They noted that it appeared as a black flaky solid. Polypyrrole, like most conductive polymers, is generally insoluble in both aqueous and organic solvents. There are a few organic solvents that will dissolve polypyrrole, but not effectively or efficiently. There have been efforts to overcome this insolubility issue by functionalization of polypyrrole, mainly on the nitrogen in the aromatic pyrrole ring. This hydrogen tends to be very reactive compared to the 3 and 4 positions, so it's much more easy to substitute the hydrogen off of the aromatic ring than it is or off the nitrogen instead of off of the hydrogens that are on the aromatic ring. Currently, there are two very common ways to polymerize pyrrole to create polypyrrole, and that's chemical oxidation and electrochemical oxidation. Um, Under chemical oxidation, the pyrrole is polymerized using FeCl3 or other similar iron or copper salts. The exact mechanism of this polymerization reaction is highly debated. As I just mentioned, polypyrrole can also be polymerized or synthesized through electrochemical means as well. This is accomplished through cyclic voltammetry or chronocoulometry. Generally speaking, both methods create a radical pyrrole monomer, and then another monomer is generated, so we have two of them. They then combine and they propagate. As they propagate, it gets kind of messy. There's a lot of cross-linking that occurs, and it's not very regioregular, so if there had been any side groups on this, it would not come out to look like, it would not be perfectly repeating or in line. It would more than likely just be a random pattern depending on how the radical was attached onto the aromatic pyrrole ring. It should also be noted that in the electrochemical method, polymerization, it generally produces polypyrroles that are, as I just mentioned, lower regioregularity, but also lower crystallinity. Um, Polypyrrole and its derivatives generally have a melting temperature over 300 degrees Celsius, and their conductivities range anywhere from 10 to 50 Siemens per cubic meter. Interestingly enough, they're also deemed mostly biocompatible. Their crystal packing behavior tends to be face-centered cubic or hexagonal close packed, and due to their insolubility, polypyrrole derivative and their derivatives are not typically solution processable. As I mentioned before, there are a few derivatives that allow it to be more easily solution processed, and some of them actually even allow it to become soluble in water, which is a big deal for conductive polymers. So while the solubility limits the industrial production and usage of polypyrrole, a common method of processing polypyrrole is through electrodeposition. This is utilized to protect metal surfaces against corrosion. Additionally, in the medical field, they also use this as a coating for gold nanoparticles for detection and indication of cancer cells. So while polypyrrole and conductive polymers are a very interesting class of polymers, there's a lack of understanding between their microstructure and the resulting material properties. So optimization and of these properties and gaining a better understanding of how the microstructure actually affects these properties could lead to more affordable and better quality electronic devices.